Hello, my name is James Stevens. I'm a PhD student in scientific computing at the University of Illinois in Urbana-Champaign, and today I will present my dissertation research on program transformation and code generation for developing, modeling, and optimizing GPU programs. This recording is not live, but it will be essentially identical to my thesis defense. I'd like to recognize other researchers who have contributed to this work. I want to thank my advisor, Andreas, for his continued assistance and his advice, and especially his time. I also want to thank my thesis committee who have helped me plan and assess my research. Matt and Kaushik are two grad students who have made significant contributions to the programming system I'll be discussing. And finally, I want to acknowledge a team of undergraduate students that I recruited to help build the user interface I'll be discussing later. Let's begin. High-performance computing is essential for solving lots of problems in science and engineering. And one thing that makes this challenging is that the computing landscape includes widely varying, changing architectures, in particular coprocessors like GPUs. Manually optimizing programs is slow and error-prone, and fully automated systems don't reliably match the performance of hand-tuned code. So, a question underlying all of this work is, can we obtain benefits of both fully manual and fully automated approaches to program transformation and optimization using partially automated human-guided strategies? With this in mind, we present three mechanisms to assess these challenges: a programming system for code generation, an approach to constructing customizable black box performance models, and a visual user interface for transforming and analyzing programs. First, I will discuss our formal dependency verification and loop nesting semantics in our code generation framework. I'll first give a quick example to introduce our programming system and also motivate the rest of this contribution. Loopy is a programming system for array computations that provides code generation for GPUs and CPUs. A key way that it facilitates program optimization is by separating the specification of mathematical intent from efficiency or performance decisions, and it also allows a programmer to avoid dealing with computational minutiae, and you'll see that in this example. Suppose we want to solve the wave equation at the right using a 5-point finite differences stencil. We create a program performing this computation by first specifying a statement and a domain. The statement describes how each element of the two-dimensional array is computed, and the bounds on the index variables are provided in the domain. Without any specification of the algorithm, Loopy would generate code that computes this with two nested for loops over the x and t domains. To specify the algorithm, our system enables a large number of program transformations, and here are a couple of examples. Suppose that we want to parallelize the X loop across threads, and in doing so, we want to exploit two levels of parallelism. So to do this, we split it into two nested loops, X outer and X inner, and then we use the tag inames transformation to parallelize each of these loops. The compute abstraction we're targeting is OpenCL, so we'll express two levels of parallelism which it allows. This transformation parallelizes the inner X loop across threads within an OpenCL thread group and the outer loop across separate thread groups. You can see in the generated code, this eliminates the X loops, and our indices now contain OpenCL thread identifiers. Those are the GID and LID variables. Are our dependencies satisfied? This is a key question, and if you look at the stencil at the right, the bottom element depends on the other four. And it turns out The answer is no. The dependencies are not satisfied because independent threads are iterating through this T loop, and if one thread lags behind its neighbor, it will use the wrong value to compute its result. We could fix this by adding barriers inside the loop to synchronize threads. So in this case, we might have been able to answer this question with a manual observation, but things can get a lot more complicated. Suppose we wanted to apply a diamond tiling strategy where we tile the domain as shown on the right, which allows the tiles in each horizontal row to execute independently. Then we might also have some local parallelism inside the tiles. In this case, a very precise ordering of statement instances would be required for correctness, and likely for performance as well. Prior to this contribution, our system had no way to express this kind of dependency or detect violations, and no way to guarantee a desired loop nest structure. And in case you're still hoping to detect dependency violations by just looking at the source code, here is a preview of the OpenCL after we apply a diamond tiling transformation. Good luck. So this example illustrates the importance of expressing dependencies which are well-defined, operate at the level of statement instances, that survive transformations, that can be automatically checked for violations, and that are user accessible. Loopy uses a polyhedrali based approach to representing programs. Some characteristics of the polyhedral model of computation are summarized here. Statements are executed over points in a polyhedral iteration domain, which is bounded by affine inequalities. This enables mathematical reasoning about execution order, dependencies, correctness, and transformations, which facilitates automated code transformation. Compared to our system, many polyhedral tools take a more automated approach to transformation and optimization decisions, as well as identification and enforcement of dependencies. These approaches typically determine a program ordering by minimizing an affine objective function under the constraint of satisfying all dependencies, which is expensive. While more automated approaches may require less work on the user's part and less user expertise, you sacrifice control over the optimization process and visibility into the decisions that are being made. One polyhedral system that gives more power to the user is AlphaZ, which expresses a program using alpha expressions. This approach does allow the user to exert some fine-grained control with transformations, but it's very abstract and transform code is non-trivial to write. In terms of control granted to the user, chill and dace lie somewhere in between AlphaZ and the more automated approaches. Both have a more restrictive program representation than our approach. Chill has an index-based interface that is more expert-focused. Dace is built around their stateful data flow multigraph representation, which requires rewriting code to use. Their graph representation expresses data dependencies and high-level control flow and is transformed by graph transformations. I'm only giving a quick summary here, but there are more details in appendix slides and also the dissertation. Now I'll discuss our approach to specifying formal, verifiable dependency semantics that are exposed to the user. First, here is a key distinction. A statement is an assignment to a scalar or scalar array elements that is executed over multiple integer points in a polyhedral domain. A statement instance is a single instance of execution of that statement for a single integer point in the domain. And in our wave equation example earlier, we specified a statement that that includes iteration indices x and t. And when we execute that statement for one particular pair of x and t values, that is a statement instance. We define dependencies as happens before relationships between statement instances. Internally, we will represent and reason about dependencies by using mappings involving statement instances and lexicographic orderings, as you will see in a moment. These kinds of representations have been used in other polyhedral systems. Some key things that distinguish our approach are the way dependency handling is exposed to the user, the way we handle dependencies when determining a program order, and also a new procedure enabling us to reason about correctness of a generated program ordering in a generalized OpenCL compute abstraction with local and global barriers. You will see all of this in a moment. Suppose that statement N depends on statement M in some fashion. We define this dependency as a relation mapping instances of statement M to instances of statement N that must occur later. And formally, we represent each statement instance as a tuple containing a unique statement identifier and a set of values for the sequential loop indices surrounding that statement. As an example, here's the dependency for the 5-point stencil we've been discussing. So here we're using 0 as the identifier for this statement. And the way to think about this is statement instance 0x prime t prime happens before statement instance 0xt if either t is 1 greater than t prime and x is between x prime minus 1 and x prime plus 1. That's the dependency on these three center elements. Or t equals t prime plus 2 and x is the same as x prime. That's the dependency on this from the top to the bottom element. In order to check whether a dependency between two statements has been violated by a given program ordering, we construct a pairwise statement instance ordering, or SIO, which represents the ordering of these statement instances as a mapping from each instance of statement M to all instances of statement N that occur later in the ordering. We then have two relations that we can compare. We have the dependency mapping, which maps statement instances to other statement instances that must occur later. And we have the SIO, which maps statement instances to other statement instances that actually do occur later in the program. So we just need to make sure that the former is a subset of the latter. Now I will describe how we actually construct this pairwise SIO. Given an ordered program, we first build three pairwise program schedules that together express the ordering of statement instances. Each of these is a relation mapping statement instances to points in a lexicographical space. The lex space is just a set of integer tuples on which we're going to impose an ordering. We refer to the first mapping, pthread, as the intra-thread schedule because it describes the ordering of statement instances executing within the same work item or thread. We create this by examining the program structure containing the statements, and notably, since we're describing execution within the same work item, we can ignore barriers and parallel execution for now. Then we create the intra-thread statement instance ordering by composing pthread with this relation at the bottom, othread, which is the relation that imposes an ordering on the points in the lexicographical space. And it does that by mapping each lex point to every later lex point in the ordering. That gives us the intra-thread SIO, which maps each instance of statement M to all instances of statement N that occur later, assuming these instances are all within the same thread. Here's where it gets a little more interesting. Next, we want to describe the ordering of statement instances executed by different threads running independently within the same work group. This ordering is mediated by local barriers. So, for example, since we're assuming statement instances are executed by different threads, if there's no barrier between them, they should map to the same point in lexicographic time, because we can't know that one will execute before the other without a barrier. So look at the pseudocode on the left. Here we have 13 statements and a for loop and a few barriers. And we want to map each statement instance to an integer tuple representing a point in a lexicographical space. The first two statements, 0 and 1, should map to the same point since there's no barrier between them and we don't want to impose an ordering. Then we hit a barrier. So statements 2 and 3 need to map to a later lex point. So we map them to 1, 0, 0. For now, you can think of the points in lexicographical space as being ordered in the standard way so that the most significant value is on the left and the fastest updating dimension is on the right. But keep in mind that we can actually impose any ordering we want on these points, which is going to be important in a moment. So continuing through the program, we hit a for loop over variable I. And we add an I to the second dimension of the lex tuples inside the loop to capture the sequential iterations of the loop. So on the first iteration, I is 0. On the second, I is 1, and so on. Then we hit a barrier inside the loop. We increment the third lex dimension from 0 to 1. And then we leave the loop, and we increment the first dimension from 2 to 3. Also notice at the bottom, when we find a loop without any barriers inside it, we map statements 12 and 13 to the same point in lex space as 10 and 11 because there isn't any barrier, so we don't want to impose an order. Now, notice something that happens at the beginning of this loop. On the first iteration, I equals 0. So S4 maps to the point 2, 0, 0. But S3 maps to 1, 0, 0. So if we were to impose the standard lexicographical ordering on these points, S3 would happen before S4. And we don't want that on the first iteration of the I loop because there's no barrier between these two statement instances. The same thing happens on the last iteration with statements 7 and 8. On the last iteration, statement 7 maps to 2n1, which would come before the point 300 in a standard lexicographical ordering. And there's one more notable issue. Every time the loop increments, I increases, but there's no barrier between S7 at the bottom of the loop and S4 at the top of the loop. So to avoid including these three kinds of unwanted before-after pairs, when we impose an ordering on the lexicographical space, we construct a specialized mapping that omits these pairs. And we do that by starting with the standard ordering and then subtracting off a subset of the before-after pairs that we don't want. So for all loops containing a barrier, we find this set of pairs of lex points that we don't want. And then, since we might have several nested loops, we need to take the transitive closure of this set of pairs to obtain the complete set of unwanted before-after pairs. Then we subtract that from the full mapping containing all the pairs, right here. And then we compose that with p group to create the intragroup SIO. And as the note at the bottom says, the transitive closure of this relation here is not guaranteed to be quasi-affine. So when necessary, we use an over-approximation that is guaranteed to be a superset of the transitive closure. Note that since we're subtracting this over-approximation, it can only cause us to under-approximate the true set of before-after statement instance pairs in the program. So it won't cause us to fail to detect a dependency violation. We create the global statement instance ordering in the same way, except using global barriers. And then, to get the complete pairwise SIO, we intersect the intra-thread and intra-group SIOs with a relation mapping all instances of statement M to all instances of statement N assigned to the same work group. And then we also intersect the intra-thread SIO with a similar relation mapping all instances of M to all instances of N assigned to the same work item. I just discussed how we formally capture the ordering of statements in a program, but how does that program ordering get produced in the first place? We refer to this mechanism as the linearizer. It generates the ordered program from an unordered program representation, the dependencies, and also the loop nest constraints, which I will discuss next. Traditional polyhedral scheduling involves an automated process that minimizes some objective cost function while obeying all dependencies, which can be expensive and opaque to the user, as I mentioned earlier. Instead, our approach avoids enumerating all possible orderings of statement instances, and instead we have the linearizer operate at the level of statements. Efficiency is the primary reason for this. Also, statements may be reordered later anyway during compilation and out-of-order execution. Now, to guide the linearization process toward a program that does satisfy the dependencies while maintaining a low-cost linearization process, we give the linearizer a directed acyclic graph, or DAG, of statements representing a simplified version of the dependency relationships at the statement level rather than the statement instance level. So if dependencies, which are expressed in terms of statement instances, between two statements meet our specified criteria, we create an edge between those two statements in the statement DAG. Again, in the interest of time, I won't go into these criteria right now, but all the details are in the dissertation. So earlier I mentioned the importance of being able to precisely express and enforce loop nest structure requirements. We address this with an additional component of this contribution. This is important for a number of reasons. Of course, the loop nesting structure affects performance, but also a particular nesting structure may be a prerequisite for a particular transformation. For this reason, we have created a mechanism to represent nesting constraints that are well-defined, that survive transformations, that are enforceable, and that can be concisely expressed. Our approach is to let the user express a must-nest set of loop pairs and a must-not-nest set of loop pairs, and these constraints are satisfied by a program if all of the must-nest pairs are present and none of the must-not-nest pairs are present. And also, each tier of a nesting specification may contain a set of loops. The example at the bottom shows how we could express that the K loop must be nested innermost by stating that K must not nest outside of not K. That is, any loop that isn't the K loop. To demonstrate our semantics formalizations, we use them to express and enforce the dependency in a diamond tiling transformation procedure for the finite differences example. You can see here how we apply the dependency mapping that was shown earlier. First, we create the map, and then we apply it to the statement that we've creatively named statement. And here the statement depends on itself. Then, to apply the diamond tiling strategy, we create a mapping from our original loop indices T and X to 5 new loop indices, and then apply the map domain transformation. I realize it's not obvious what happens to the indices in this mapping, so here is a visualization. The nesting order of these loops is still unspecified at this point, but it's easier to think about them as if it is. The outer loop is going to be the TT loop, which iterates in the T direction through pairs of rows of tiles. Then, within that loop, The t-parity loop alternates between even and odd rows. Inside that, the tx loop iterates across each row of tiles in the x direction. And then the itx and itt loops iterate over individual elements within each tile. Like I said, we haven't imposed an ordering on the loops yet, and these are visualizations we created by specifying both incorrect and correct loop nest orderings. The color fade from blue to yellow shows the order that the results were written, and the ordering we want is on the left. So up to this point, these loops are still all sequential. These two transformations create two levels of parallelism so that each tile in one row is executed independently by a separate group. And then within each tile, iterations of the itx loop are parallelized across threads within a group. To ensure that our dependency is satisfied, we add a global barrier and a local barrier using the add barrier transformation. This synchronizes the groups and threads so that they iterate together in lockstep. Then we add a must-nest constraint on our remaining sequential loops, and we verify that our dependency has not been violated. Note that our original dependency was expressed in terms of x and t, and as each of these transformations is performed, we also perform any necessary transformations or changes to relevant dependencies. So this dependency, for example, is now expressed in terms of the new loop indices. Finally, here are some results for this particular transformation chain for different problem sizes. Note that this memory throughput is a lower bound because we're only counting the footprint of the data accessed. Also, it's worth noting that we obtain the stats used to compute this flop rate and bandwidth using the automated stats counting routines from the second contribution, which I'm going to discuss a little bit later. All right. To show that our program semantics can be applied to a complex application-level benchmark, we also demonstrate their use in transforming subroutines taken from the lower upper symmetric Gauss-Seidel benchmark in the NASA Advanced Supercomputing Parallel Benchmark Suite. This code is a simulated CFD application, and it uses successive overrelaxation to solve a block diagonal system. And the system that arises from a finite, finite differences discretization of Navier-Stokes equations in 3D. A Fortran implementation of the benchmarks is available, and the subset of that code that we're addressing is shown on the left. This is computed within one step of the SSOR solve. So inside these loops over the K and J domain indices, these two subroutines create the Jacobian and then solve a block lower triangular system. What you can't see in this snippet is that inside each of these subroutines, they loop over the third dimension of the domain. That's the I loop. The dependency structure of this computation is depicted on the right. The solution for each ijk element depends on the previous result in the j, k, and I directions. I is not shown here, but you can imagine this in 3D. One way to expose some parallelism here is to compute these indices in a wavefront access pattern. So as long as all of the indices in the previous diagonal wavefront have been computed, the indices in the next one can all be computed independently. And that's the approach we will demonstrate. This example also highlights an important capability of our programming system. It can ingest Fortran subroutines to represent them as Loopy kernels, and that is useful here. Then we need to create the dependencies. There are over 500 unique pairs of statements related by a dependency, so I will only show two examples. The first example is a dependency where a statement in the subroutine computing the lower triangular solution depends on a result computed by the statement in the Jacobian subroutine for the same ijk index, and that is expressed with these constraints here, saying that j equals j prime, k equals k prime, and I equals I prime. The reason there are two different I variables here is that each of the subroutines has its own separate I loop. And then the second example is a dependency within the block lower triangular solve, where this statement uses a result computed at the previous k iteration, which is why we specify that k equals k prime plus 1. To use the wavefront access pattern that I described earlier, we next create a mapping from the original loop indices to the new ones. And then we specify a loop nest constraint, ensuring that the loop over the waves nests outside any other loops. Again, this is one of our heat maps showing the order that solution elements were computed. Then we parallelize the wavefront across workgroups and add a barrier to synchronize them in lockstep. Here are some results. Note that in calculating the bandwidth in this case, we apply a different performance model than before, counting each memory access as it happens rather than just the footprint of the accessed data. So to summarize, with these examples, we demonstrated how a user can express and access dependencies using our representation, that we can automatically transform these dependencies as program transformations are applied, that our dependency and program ordering semantics enable automatic checking for violations in a transformed program, which is key in situations where a generated program has a level of complexity that prohibits manual dependency checking. We demonstrated how a user can express precise constraints on loop nest structure using our semantics, and that we can apply all of this to a complex application level benchmark which can be ingested into our programming system. Next, I will discuss the second contribution, a mechanism for balancing accuracy and scope in cross-machine black box GPU performance modeling. This will be a very brief summary of some highlights since the full details can be found in the paper. Our goal with this contribution is to model, interpret, and predict execution times in an automated, architecture-independent fashion. We constructed a framework where a user can model execution time or any kernel feature as a custom function of kernel features and parameters. A kernel feature is just a quantitative characteristic of a kernel. For example, the number of 32-bit floating point multiplications performed. And the feature is parameterized by the relevant iteration domain size parameters. The machine-dependent parameters in the model relate features to execution time, and we find those by fitting the model to data from a custom set of micro benchmarks. We demonstrated two different kinds of models in the paper, and each of these models divides workload cost into three categories: global memory access, on-chip work, that's arithmetic and local memory access, and overhead. Each of these individual cost categories is a sum of kernel features weighted by cost parameters. Then we construct a linear model simply by adding all these costs together. And we also constructed a nonlinear model that allows for modeling of overlap between global memory access and on-chip work, which I will discuss further on the next slide. So what we're aiming for here, the model we're aiming for is shown at the bottom, where we model execution time as the overhead plus the maximum of global memory cost and on-chip work. However, our models have to be differentiable, so we use this s-hat function to approximate a step function, which serves as a mathematical switch to select between these two costs, depending on which is greater. This model supposes that these two costs can be fully overlapped, but you could alter S hat slightly to model partial overlap as well. To show that this kind of model can capture overlap of global memory access and on-chip work, we were able to fit it to the feature data from an experimental kernel where we vary the ratio of on-chip work to global memory access. For example, you can see in the first chart that as we increase the ratio, the execution time remains flat at first until the point where the on-chip work becomes more expensive than the global memory access, and then the execution time starts increasing. To evaluate our approach, we modeled execution times of multiple variants of 3 different computations on 5 GPUs to determine, for example, whether our models could accurately determine the best performing variant. The overall relative error across all measurements was 6.4%, and in 13 of the 15 cases, the models were accurate enough to correctly rank all variants by performance. We were also able to show several cases where the models provided insight into the sources of computation cost. Further details of this are all available in the paper, but I will briefly show our 3 sets of results. Here are the results on 5 GPUs for 2 variants of a matrix multiplication. In these charts, each color corresponds to a different variant of the computation. The dotted line shows the modeled execution times, and the solid line shows the measured execution times. And error percentages for each GPU are visible in the charts, and percentages for individual variants are in the table. And you can see how these results predict well enough to help select between variants. I'm just showing these briefly, and if you'd like more details, please read the paper. These are variants of a component of a discontinuous Galerkin computation, and these are variants of a finite differences stencil. Finally, I will discuss the third contribution, a visual user interface for code transformation, analysis, and optimization. As you can tell from the discussion so far, composing a program transformation chain is technical and can involve a lot of experimentation and trial and error to find the best program variant. We'd like to make that easier and more interactive. This has been tried before. Here are some images of a selection of existing interfaces with similar goals, that is, exploring an optimization search space of semantically equivalent variants of a general purpose program by applying transformations. There are details on each of these in the appendix and also in the dissertation, but I wanted to display what some of them look like, especially the geometric diagrams that they have users interact with to perform transformations. So here are some of the key ways that we are building and improving on these approaches. We provide users with a fine-grained search space with integrated program statistics and transformation information. We enable transformation through direct interaction with the source code, without manually writing source code, of course, which we believe is valuable since this representation of program behavior is already understood, and also because that's often the representation a developer is already focusing on when they decide to make a transformation. And we enable easy deployment of a modifiable program generation script that uses our underlying programming system, so the deployed program representation inherits all of the advantages of this system. We've proposed a number of criteria that a successful interface should meet. One is that source code and transformation code should not be manually written. So we enable the user to specify the intent of the program with high-level math, and we automatically generate source code with Loopy. We allow the user to apply transformations through direct interactions with the source code, and to enable the user to avoid manual coding even after a program is deployed from the interface, we deploy a source-generating transformation script that can be easily modified later. Another key criterion is that the system should expose a navigable search space of program variants, allowing a user to compare multiple transformation paths and reason about the consequences of transformations. Here you can see an example interaction with our visualization of the program variant search space. The nodes represent program variants and the edges represent transformations. And then by hovering over a transformation, you can view information about it, and by hovering over a node, you can view program stats like execution time, flops, bandwidth. We set forth a number of design objectives. I will discuss a few of them briefly. First, we wanted to enable direct interaction with the source code, and one way we evaluate the benefit of this is by comparing the number of user actions required to perform a transformation by interacting with the source code and also performing that same transformation using a menu of transformations. I'll display a table that makes this more concrete later. But here you can see a couple of important differences between these two cases. So to perform a loop splitting transformation, on the left, we use the drop-down menu and have to find the transformation we want among many other options. Whereas on the right, we just click on the loop variable and choose from a small set of transformations that are relevant to that particular code element. Then when we enter parameters for the transformation, on the right, in this case, we have fewer parameters to enter because the interface already knows which loop we clicked on when we initiated the transformation. To maintain scalability with respect to the number of program variants in the search space, we enable hiding of arbitrary subsets of the search space. You do this by selecting nodes that will be the start and end points of hidden sections. In this way, locating a particular variant scales with the number of unhidden variants, which can be kept much smaller than the full search space. We enable collapsing of code blocks for the same reason. Programs generated within a larger code library may result from complex machinery, making them difficult to reproduce as a standalone code, including through this kind of interface. So we enable in-situ exploration of these programs by importing them as is directly into the interface using the simple function call shown here. We also provide complete reproducibility of a given search space for subsequent experimentation. And for program deployment, a user can export both the source code and a transformation script that applies all the transformations they performed in the interface to generate the program. To enable us to quantify the extent to which our system succeeds in attaining those goals, using measurements that can be collected objectively, we count the number of actions required to perform certain tasks. 4 of these actions are commonly counted in HCI. Those are position, select, text, and quantify. Since 2 of our objectives concern the immediacy of interaction with the source code representation and also the search space representation, we qualify some position actions as independent of visual representation. That's what IOVR stands for. And this means that the cursor must be positioned at a location that is independent of the visual representation of the object being manipulated. I'll just highlight a couple items to notice here. First, we can now quantify the comparison we made earlier between the two different ways of performing a loop splitting transformation, and see that doing this by interacting directly with the source uses fewer actions and also avoids position actions that are independent of visual representation. Another thing to notice is the scaling factors. For example, when interacting with the search space, bringing an arbitrary non-hidden kernel node into view scales with V star instead of V. So if you keep the number of unhidden variants manageable, which in our experience is easy to do, a search space can grow very large without severely impacting the cost of interacting with it. Finally, we demonstrate practical application of our interface by using it to optimize the computation demonstrated in the Loopy paper cited here, which computes the volume term in the semi-discretization of Euler's equations used in a weather prediction model. This transformation chain is complex, and it demonstrates a variety of Loopy transformations, including kernel merging, vectorization, prefetching, parallelization, conversion between imperative and substitution-based code, and several others. In total, there are 125 transformations. And here are the results. What this demonstration shows is that our interface provides the transformation capabilities necessary to produce a highly optimized application kernel, in this case, achieving near theoretical hardware peak. Here is a final screenshot of the user interface. And here is a summary of the key contributions I've presented today. Taken together, our programming system, our approach to performance modeling, and our transformation interface support the attainment of maintainable, high-performance scientific codes across varying parallel architectures. We just discussed most of the points listed here in detail, so I won't read through them. Thank you for listening. Before ending, I just want to express my appreciation to everyone who has been supportive in many ways to me over the past few years. I appreciate you all, especially my wife, Catherine. Being a doctoral student is challenging, and I think almost as challenging is being married to a doctoral student. She's been amazing. This concludes the talk. Thank you.